Now we are going to study about optical isomerism, optically active compound, optically inactive compound. All these features I'll be explaining to you in this video. Now, what what is optical activity? Optical activity is basically the capacity of a molecule to rotate plane polarized light. I'll explain it to you through a figure. See, normal light has vibrations along all directions. When this light is passed through Nicol prism, when this light is passed through Nicol prism, this Nicol prism, then we get only oscillations in a particular direction. We get such kind of light in which only vibrations are happening in particular direction. So this is called as plane polarized light. This is ordinary light. This is ordinary light, and this is called plane polarized light. So what happens is plane polarized light. What happens when this light is passed through a solution, through a solution of organic compound, solution of organic compound. All right. So what happens is if a compound is optically active, then it rotates the solution when light comes out of this. Either it comes out like that. There are three possibilities. What are these? Either plane polarized light will come out like that. It goes like that and it comes out the same way. That means the solution has not rotated plane polarized light. That means the organic compound whose solution we have taken is optically inactive. That means no rotation of plane polarized light means organic compound taken in the solution is optically inactive. Next, what could happen is that the plane polarized light coming out of this either rotated towards right or this is rotated towards left. So if it is rotated towards right, that means the organic compound we have taken in the solution is dextrorotatory and optically active. Next, if it rotates towards left, plane polarized light is rotated towards left, then that means the organic compound we have taken is levorotatory and optically active. That means you can summarize, if solution of organic compound rotates plane polarized light, the solution or the organic compound we can say is optically active. If plane polarized light is not rotated, that means the compound is optically inactive. If plane polarized light is rotated towards right, the organic compound is dextrorotatory, and if or the plane polarized light is rotated towards left, that means the organic compound is levorotatory. All right, and the degree of rotation is called as angle of rotation, and we have a measurement for that, that is specific rotation. For specific rotation we have a formula that says alpha equals to theta upon c by c into L. That means theta is angle of rotation, c is concentration of the solution we have taken, and L is length of the polarimeter tube. The concentration is taken in gram per ml, and if we put all these values, we get a ratio of angle of rotation per unit concentration per unit length of polarimeter tube, which is known as, this ratio is known as specific rotation and represented by alpha. That is the formula we have taken here. Now, I have already explained that a compound which rotates plane polarized light is optically active. So, condition for a compound to be optically active, when we considered n number of molecules, we found out that if molecule is unsymmetrical, if molecule is unsymmetrical, it is optically active. If molecule is symmetrical, it is optically inactive. So in Greek, for unsymmetrical thing, the word is chiral. So if a molecule is chiral, it is optically active. If molecule is achiral, it is optically inactive. Chiral means not symmetrical. Achiral means symmetrical. For example, we have taken few things here. The alphabet C. If you take alphabet C and its mirror image, alphabet C and its mirror image, they are not superimposable. So the alphabet C and this mirror image can be a set of enantiomers or optically active compounds. So no symmetry is there. That is why they are non-symmetrical and non-superimposable. Whereas A has plane of symmetry. So this molecule and A, its mirror image, are superimposable. Superimposable means, let me explain it to you like this. If you have something like this, let me put this hand out here. This is unsymmetrical and its mirror image, this molecule, if we take a molecule like this, it is dextrorotatory, then its mirror image, this hand, will be levorotatory. So two molecules which are mirror image of each other are called as enantiomers. So one molecule is this and its mirror image is this molecule. So these two molecules are known as a pair of enantiomers because they are non-superimposable mirror image of each other. So a pair of compounds which are non-superimposable and mirror image of each other are called as enantiomers. So this pair is known as enantiomers. So I have given you a small example, and just remember, if symmetry is there, molecule is achiral and it is optically inactive. If symmetry is absent, it is chiral molecule and it is optically active. Next we have out here is chiral carbon. Chiral carbon is a carbon which is connected to 4 different groups. As we have taken in this example, you can check out one, this carbon, the carbon at the center is stereo center or chiral carbon. This is connected to 4 different groups: CHO, OH, CH2OH and H. So all 4 different groups are there. So this carbon at the center is known as chiral carbon or stereo center. Similarly, you can check out here 4 different groups are connected. So this is again a chiral carbon at the center. So chiral carbon, if we have one chiral carbon, the molecule is unsymmetrical and it is optically active. So just remember, if one chiral carbon, the molecule will always be optically active and it will form a pair of enantiomers. That is, compound and its mirror image will be non-superimposable, and compound and its mirror image form a pair of enantiomers. Alright, so I have tried to explain everything in detail out here. Hope you loved it. Thank you so much.